Okay, thank you, Leon. It's always a pleasure to be here at Santa Barbara. I'm coming to KITP from the time it was up in Ellison Hall. And a lot of the things I'm going to talk about, I've learned from people here, and there are many experts in the audience, but so it's going to be very simple for at least part of the talk for all of you. But anyway, bear with me. This is addressing the beginning graduate students, I hope. All right. All right, so I'm going to, so as the title says, I'm going to talk about two topics that are rarely ever in the same talk, although that's been happening in the last few years. Superconductivity, the type of materials that we might be interested in the workshop going on right now on gapless quantum states, and black holes of the type that might be of interest to the previous string theory workshop. So I'm going to try to bring them together in some sort of a historical view of some important discoveries in physics, starting in 1865 on just what is quantum entanglement, and then going on to superconductivity in black holes. And I'll sneak in some recent work towards the end, but most of it will be just a survey of things that at some point or other you may have learned about earlier. 1865. Okay, exactly. Quantum entanglement. Why is that 1865? Good catch. All right, so 1865 is when Kekulé, a German chemist, had a spooky dream, according to Wikipedia. Of course, and he basically is the chemist who figured out the structure of benzene. So at that time, quantum mechanics, of course, hadn't been invented, but people had learned about bonding, and the fact that each carbon atom has 4 bonds and covalent bonding had been taking shape in chemistry. But this posed a problem in the structure of benzene because each carbon atom has only one remaining bond to form. This is the pi bond. And if it picks the neighbor in this 6-fold ring, then that would break the symmetry of the ring, and benzene would not be a perfect hexagon. And so Kekulé said he had a daydream of a snake seizing its own tail, and proclaimed that, in fact, the word I believe he used was resonance, that there are 2 configurations, this one, and the benzene is a resonating superposition of both of those. Of course, now quantum mechanics tells us that this is really a state of 6 entangled electrons, in which you have 2 distinct states, this one, and they're entangled together in benzene. All right, but the real introduction of quantum entanglement, 1935, is a fairer way of putting it. It's probably this paper by Einstein, Podolsky, and Rosen, this was written at the Institute for Advanced Study, and it kind of expressed a skepticism of Einstein on the basic principles of quantum mechanics. And the reason for skepticism was a beautiful thought experiment that was proposed in this paper. The word entanglement was not introduced till much later, was never used in this paper. And the idea of EPR was that, okay, if maybe you're all fine with entanglement on the microscopic scale, because things behave bizarrely on the microscopic scale. So if you take something as simple as a hydrogen atom, where you have 2 electrons, and there's 2 possible states of the electrons, one in which the left one is up, and the other one in which the left one is down, whereas the right electron is pointing in the opposite orientation. And quantum mechanics tells us that it's really the superposition of these 2 states. These 2 electrons are entangled. Their spins are entangled in this manner. Sorry? Yes, what did I say? Did I say hydrogen atom? Sorry, thank you, hydrogen molecule. All right, but the thought experiment was, well, suppose you could separate the 2 electrons without disturbing their spin, then they would still be entangled. And so now you would have some really truly long-range effects where the 2 electrons are entangled, and if you looked at one and found it to be up, then instantaneously, and this was the part that Einstein didn't like, the other electron would be down. And this is what we call spooky action or distance. And I always wondered, did Einstein really actually use these words? And the answer to that, surprisingly, is yes, as I learned from Ahmed Al-Meiri. This is a letter that Einstein wrote to Born in 1947, and that's spooky action at distance in German. I won't try to pronounce it. But anyway, he said he cannot seriously believe in quantum mechanics, the theory, because the physics should represent a reality in time and space free from spooky actions at a distance. All right, well, he had the right idea. He put his finger on really the most strangest part of quantum mechanics. And physics is indeed local. But what is not local, we now accept, is just the wave function. The state of the electrons doesn't belong to the left electron or the right electron. It just belongs to both. So nothing is traveling because the wave function wasn't localized in either place. So once you accept that, the non-locality of the wave function, which is really not a physical object, you can never observe it. You can only look at its consequences and its correlations. All the consequences are completely local, but the wave function is an intermediate concept which we view as non-local. Anyway, that's my way of understanding it. And of course, today, the thought experiment is far from a thought experiment. Here's New York Times declaring it to be real. This is an entanglement of photons, not of electrons. Electrons are much harder to entangle, 1.3 kilometers apart. And now this has been done, on satellites in space and so on. So there's no question that spooky action is real today. So that's about quantum entanglement of a pair of electrons. And of course, since then, quantum entanglement has gone from a philosophical sidelight to a central role in physics. Most famously, of course, with qubit devices or quantum computers, if you want to call them that. But I will say nothing about that. So in this case, you're really very carefully controlling quantum degrees of freedom to compute something useful or deduce something useful about quantum mechanics. That's not what I'm going to talk about. I'll talk about how, in many instances, in nature itself, in many, especially in lots of interesting materials, there's entanglement, which in some precise sense can also be viewed as long range. And that'll be the first part of my talk. And then there's the famous Hawking's black hole quantum information problem, which I won't really directly address. I'm sure you've heard from other Colloquium speakers on that. But there's certain aspects of Hawking's black hole theory, which has been clarified by a deeper understanding of quantum entanglement. And somewhat remarkably, it's the same model that has made progress in certain aspects of both point 2 and point 3. That'll be the main theme of my talk. Okay, so that's quantum entanglement. Now let's move forward from 1865 to 1870, which is the start of statistical mechanics. So the basic ingredient in statistical mechanics actually goes back to thermodynamics from Clausius, where before there was an understanding of the microscopic or molecular nature of matter. This is a perpetual motion machine built by Lisa, his daughter. Okay. So very clever engineers figured out that there is some quantity called entropy, which is on par with temperature and pressure and volume, which everybody has, and this quantity cannot decrease. But our understanding of entropy really made a huge step forward in 1870 with Boltzmann, where he made a connection between the molecular nature of gases and entropy. And he identified entropy, as it says on his gravestone in Vienna, as the logarithm of W, where W is the number of possibilities of the atomic positions consistent with the macroscopic state of the object under study. Remarkably, Boltzmann formula continues to hold also in quantum mechanics. You just have to replace W by the density of many-body quantum states. This is a much more precisely defined quantity. If you could just solve the full many-body Hamiltonian, you just count how many states there are per unit energy interval, take the logarithm, and you get the entropy. And also, then temperature, rather than being a derived quantity, then becomes very precisely defined as the rate of change of entropy with energy. Boltzmann also made another very fundamental contribution, so the first contribution helped understand the thermodynamics, the statics properties, the equation of state, for example. The second told us about dynamics, and that's the famous Boltzmann equation. So here, Boltzmann was thinking about a dilute classical gas, like the molecules in this room, and you write the equation of motion in terms of the distribution function of these molecules, Fp, and the left-hand side is just a complicated way of writing down Newton's laws of motion. And the right-hand side is Boltzmann's innovation, which is the collision term. So every now and then there's a rare collision, and you just compute the probability that the collision occurs and put it on the right-hand side. So there's an underlying assumption here, which is that the collisions are statistically independent. So, and this is built into the fact that this depends on the product of the distribution function of the two particles colliding. So they're assumed to be statistically independent, and so after they collide, they forget there was a collision. With that one little assumption, Boltzmann, very successfully could even derive the rate of increase of entropy and compute things like I don't know if he did it himself, a lot of other people did it soon after, the viscosity of a gas, and so on and so forth. In fact, Boltzmann's equation has been so successful, it even applies almost always, even for electrons in metals. So now we're moving to a very different regime. Boltzmann was thinking about dilute classical particles, and electrons in metals are dense quantum particles. And nevertheless, the equation is essentially the same. And the only difference is these 1 minus f factors. So this is, say, a collision of two particles coming in. F tells you the probability those states are occupied. And the 1 minus f is just the exclusion principle. The outgoing states have to be empty. And this also shows you why, even in a dense quantum gas, collisions are rare, as they need to be for the Boltzmann equation to apply. Because if you're well below what's called the Fermi energy, all states are occupied, in which case the 1 minus f is 0, or if you're well above, then the f's are 0. So it's only right at the boundary that these collisions happen. And that's why, amazingly, Boltzmann's equation just still works. And has been the basis for, it's not an exaggeration to say, almost everything in condensed matter physics, say up to 1980, along with the BCS theory, I suppose. Anyway, so for example, this kind of theory describes the current flow in ordinary metals, like copper or something. So the electrons are dense, but they collide only rarely, and the scattering rate diverges as 1 over temperature squared from the electron-electron interactions. And so then from computation of Boltzmann's equation, you find that the resistivity must increase from a residual resistivity, which comes from the impurities, as T squared. So now you can ask, okay, that's great. So if temperature goes low enough, the scattering time is very long, and Boltzmann equation implies, when does it break down? Can you get metals in which Boltzmann equation doesn't apply? And you can make some sort of arguments that there's some fundamental breakdown, some kind of uncertainty principle arguments that if this time becomes much longer than what people now call the Planckian time, it's basically the only time you can make from Planck constant and temperature. As long as tau is bigger than h bar over kT, Boltzmann equation should apply. Well, at least this simple version of it. Okay, so this tells us that, even in a dense quantum gas of electrons, individual electrons, they're kind of renormalized by their environment, so we call them quasi-electrons or quasi-particles, still have only rare collisions, and you have a very simple picture of transport and really many other properties in ordinary metals. Okay, so that's statistical mechanics. Let's go to superconductivity now. So superconductivity. So that was discovered in 1911 by Camerly-Onnes, who cooled mercury down to, well, I don't know, minus 269. I don't know why I've written it that way. 4 degrees Kelvin, I guess. This is for a public talk. They don't like Kelvin. Well, apparently it was discovered by his graduate student, but anyway, so now we don't. But, and well, okay. Awful joke is that then both Carmeleon has decided he has to take the graduate student off the project. So either he was wrong, in which case time to be off, or he's right, in which case also time for him to be off. That's just a joke. It's not true. We treat graduate students much better than that these days. Anyway, so now jumping forward to 1986, 87, where you didn't have to go to 4 degrees Kelvin. You could just put something in liquid nitrogen. These are the famous high temperature superconductors, best example of which is yttrium-barium copper oxide. So it has a rather complicated structure, but the purpose of this talk, all you need to know, really don't need to know much more, that the electrons actually like to move around just on a square lattice of the copper atoms. So you don't have to worry too much about the rest of the crystal. Anyway, you take this material and you put it in liquid nitrogen, it becomes a superconductor, so there it's floating above some magnets until it heats up, and then it's no longer a superconductor. So that's a remarkable experiment that you could not have done so easily. Now you can do it in any classroom before 1987, because you needed much lower temperatures to make anything superconduct. Of course, it's been a dream for physicists to make this useful, and there are many possible applications that have been out there. But one potential killer app that I'm quite excited about is the existence of many companies now, including this company in Boston called Commonwealth Fusion Systems, who are using YBCO. So this is a tape of YBCO here, to create very high magnetic fields that will enable them to confine a plasma here for plasma fusion. So who knows whether this will work out? But I think more than any other application justifies, the search for better superconductors, maybe even at higher temperature. In fact, I think the temperature is not the big problem. Liquid nitrogen is cheap. You can easily cool it down to the required temperature. It's the quality of the superconductor, how well it can withstand magnetic fields, and so on. That needs to be improved, I suspect. There are various materials issues. Also, I should mention as an aside, there's been a lot of other sort of bad press for superconductivity lately. Yeah, I'm not going to apologize for it, just ignore it. This is the real thing. All right, so now here's a phase diagram of YBCO, where the horizontal axis is the density of electrons or holes in the copper oxygen layer, which you control by changing X, the density of the concentration of oxygen away from the layer, and temperature. This is the superconductor which is the reason for all the excitement, and in this case TC is almost 100 Kelvin here. But now I want to focus on the state above the critical temperature. Why is that? Well, if I'm going to understand why TC is so high, I need to understand what it's going into. And so that's really step one. So if you look here in the blue region and you look at various properties, you find they're not so different from copper, T-squared resistivity and so on. But in here, we have this unimaginatively named strange metal, where everything is strange, including the resistivity. Here's the resistance, which is a linear function of temperature, before it goes superconducting at 40 Kelvin or so. And this is not something you can understand from Boltzmann theory. So this has been known for a long time, and really has been the reason for certainly my interest and interest of many other people to try to understand these materials better. In particular, this linearity resistivity and many other properties. This may turn out to be the hardest to understand, but there are many other properties that are anomalous in this strange metal. And this occurs exactly where there's a high TC, hence our obsession with this region of the phase diagram. In particular, I just want to show this optical conductivity data, which is you look at the reflectance of one of the superconductors as a function of frequency of light and temperature. and you can fit that data in a manner that gives you some way of estimating this collision time I mentioned that appears in, say, the Boltzmann equation. So this collision time turns out to obey this very basic Planckian structure. And so what you notice here, quite remarkably, is that this collision time is precisely at the lower bound for the validity of Boltzmann's equation. So clearly, Boltzmann equation can't work, and we need a non-Boltzmann description of the dynamics of how current flows in this material. Okay. All right. So then we move on to black holes. You all with me, right? Then I'll put it all together. Okay. So black holes. So black holes were one of the great theoretical discoveries by Carl Schwarzschild, who died soon after in World War I, who was solving Einstein's equations of general relativity, and he found a solution of objects where if you took a mass m and compressed it down to a very small size, then inside the radius of what's called the horizon, no light would ever escape, or any matter would ever escape. It was permanently trapped in this region. Well, so for the Earth's mass, this Schwarzschild radius is 9 millimeters. So if you compress the Earth down to the size of a pea, it would be a black hole. But that seems rather implausible. And so most people just dismissed this as a theoretical speculation and not a physical solution of Einstein's equations. But of course, now we know it's more than black holes are everywhere. There's one at the center of our supermassive black holes at the center of our own galaxy with 4.3 million solar masses. And the radius is of the size of the Earth's orbit around the sun. So that's quite an amazing object. And many different probes have seen it now. And there are many other black holes, as I'm sure you know. But this still raises the question of what's inside a black hole. In fact, the matter, if you take Einstein's equation and continue to solve them inside a black hole, they would predict that the mass is even more dense than you imagined. It's so dense that it collapses to a singularity at the center of a black hole. So this was one of the reasons people were skeptical of Schwarzschild's solution. But in any case, once matter becomes so dense, you have to then worry about the quantum theory of the collapsed matter. All right, so now I bring together quantum. Now let's apply the quantum theory to a black hole. And the first person to do this was Hawking. And I'll kind of paraphrase his argument in some simple terms. We just take our famous EPR pair of entangled electrons and imagine that we separate them so that one falls inside a black hole and the other stays outside. Then quantum mechanics says that nothing happened, that they're still entangled. There's nothing physical at the horizon. There's no stop sign or anything. It looks the same as you're going through it to you, other than strong gravitational fields. But that presumably doesn't expect to spin very much. And so they're still entangled. So if I'm an observer outside the black hole, I have with me this qubit, which is entangled with a partner, at least for a little while, which is inside the black hole. So by considering this, calculations of this type, Hawking had made the brilliant conclusion that black holes, in fact, rather than being completely black, are more like black bodies. They have a temperature and an entropy. I should say Bekenstein had earlier postulated an entropy. Hawking got the precise number for it. And roughly the idea is that if I have this qubit in my hand, then it's entangled, so it's in some pure state, but since I can never access the other qubit, it's essentially a random state. And so it'll look to me that this is some kind of random state that is characterized, by the entropy. Okay. So by just looking at what's happening outside a black hole of these entangled pairs, Hawking actually computed the black hole entropy. And one of its most surprising features is that it's proportional to the area of the black hole horizon. And again, roughly you can understand that by the fact that it's entirely due to entanglement across the horizon and the number of pairs, and I think that's Mark Strednicki was the first to say this, that it's the entangled pairs on the horizons that lead to this entropy, and therefore it's proportional to the area. Okay, so anyway, and this is now, here's another gravestone. So there's a story of gravestones, where there's another fundamental law on of entropy, which is Hawking's gravestone in Westminster Abbey. I tried to go see it, but I couldn't. It was the line was too long last summer. Anyway, so Hawking computed the Hawking temperature and also the entropy. But another interesting problem, another feature of black holes is what you can call their ring down time. So imagine you have a black hole which, say, maybe swallows up a star, and as it's swallowing up a star, it gets distorted, but very quickly it will ring back to a perfect sphere and be in thermal equilibrium again. So you can ask, how long does it take for a black hole to go back to thermal equilibrium? And amazingly, you find, after this was actually computed even before Hawking, but in terms of classical gravitational variables, but when you express it in terms of the Hawking temperature, it's again this Planckian time. So that's the first hint, strange as it may seem, of some connection between superconductors and black holes. Superconductors have this collision time, which is h bar over kT, and black holes have a ring down time, which is also h bar over kT. That could be a coincidence, but I'm going to argue it's a bit more than that. All right. Yeah, so Hawking's calculation, raises this battle of gravestones because, Boltzmann said entropy is log of the density of states, whereas Hawking says entropy is the area. So are these two compatible? What are these states? What states are we talking about? Can you compute the DOV of a black hole, and is it consistent with these two fundamental formulas of physics? Okay. So I'll say a bit more about that and on the progress that's been made on that question in the last few years, towards the end of my talk. Okay. So now I'll talk about the model mentioned in the title, sometimes called the SYK model. And basically, I came up with it in working with my first student, Jinwoo in 1992. And I was very much motivated by this high TC problem in those days. And I decided that, the problem is too difficult. We just need some solvable model where you can get some metallic-like states which has entanglement of all the other, between infinite number of electrons. Boltzmann equation just doesn't account for the entanglement. It just assumes the collisions are statistically and even quantum mechanically independent, so there's no interference between successive collisions. You have to account for the interference, quantum interference between successive collisions of the microscopic particles. Anyway, so Kekule had a dream. So I said I also had a dream. Well, not true. But so it involves snakes. So there is an ancient Indian game of snakes and ladders, which is true. The British then called it chutes and ladders because snakes were too scary for the British public. But this is the origin of it. And in which there are snakes going from every point to every other point, roughly. And that's the entanglement. So that's the model. Well, no, little more precisely. Imagine you have a bunch of sites. And this picture here is actually taken right here of that's Jinwoo and Alexei Kitev. And then you occupy some fraction of them. And so these are quantum mechanical particles. So I'll take them to be fermions. And they're going to now tunnel. So the one thing I'm going to do is just prohibit any single electron from moving on its own. That's a bit unphysical, and we'll come back to that issue later. But for now, let's just imagine that the electrons can only move in pairs, or in triples or whatever. But the most important thing is that you don't allow a single particle motion. So for example, electron on site 11 and 12 could hop to sites 5 and 14. And in quantum mechanics, every such process is associated with a complex number, which I call U this, and so on. So for every order n to the fourth configurations of those 4 numbers, I can have a complex number associated with them. And so I give you a list of complex numbers depending on the physical situation I'm studying, and ask you to then figure out what are these electrons doing, what are their dynamics, and so on and so forth. But you will quickly throw up your hands. That's not solvable, because the number of possible states of the electron is 2 to the n. Even though the number of complex numbers here is n to the 4, there's a huge number of states of electrons, and n greater than, in this case, I don't know, 30 or something. You can't solve this problem. It's too hard for the biggest classical computer anyway. So what we realized back in '93 was that you could solve a problem closely related to this with one further assumption. You just made the assumption that these U's are statistically independent. So that's all. You need to assume that these U's are a set of numbers. I mean, even for a given system, they look kind of random. So let's assume there's no pattern. And so essentially this, up to probability 1, they're all statistically independent. That there's no real correlations between them. And once you assume that, you can actually solve this not only in the large n limit, but today with the help of input from string theorists, even more systematically at smaller values of n. So what do you get from this? So I'll just tell you about some of the results. So you get, what we already knew at some level in '93, what we were looking for. You're getting a toy model or an example of a state, of a metallic-like state, in which there are no quasi-particles to which you could apply the Boltzmann procedure. And the current is not carried by, if you could set this thing moving, which I haven't yet, it would be carried not by individual electron, but by some kind of entangled quantum soup. So you'd have current flowing, but no concept of single particles carrying the current. And this is the consequence of this complex quantum entanglement. So for the more technical inclined, here's the actual Hamiltonian written in terms of operators. So these U alpha, beta, gamma, delta I told you about. And these are fermions, and just the assumption is that they take them to be average 0 and some mean U. Anyway, you can solve this. So what do you get? Here's you solve it by, you can solve it in perturbation just by looking at graph expansion or other methods. You get a bunch of integral equations that you have to solve. When I first wrote down these equations, I said, okay, we'll just solve them the next month or so. 20, 30 years later, we're still learning new things about these equations. They're incredibly rich and have hiding within them some aspects of quantum gravity, as I'll try to show you. So first, one of the things we understood already in the early days, especially in this work by Antoine Georges and Olivier Parcolet, that this has, if you define a suitable collision or relaxation time, it has exactly the properties of the strange metal. The star of omega is h bar omega t. In particular, the energy scale U, this value U, which is an energy scale, doesn't appear anywhere in the form of this function f or as a prefactor. So that's quite remarkable. So that's great. So you finally have at least one model where you can solve it and see this kind of Planckian dynamics that has been observed both in the superconductors and is theoretically postulated for black holes. Okay. Then another feature which seemed to us to be a bit of a bug when we first discovered it, but it's not. In fact, it's one of the most interesting features, is that this model has a 0 temperature entropy. Now, this is not to be confused with a ground state entropy, which is something quite different. What 0 temperature entropy says is that if you look at all the energy levels, the D of E, then the spacing between these levels is exponentially small. So the density of states as E goes to 0 is E to the n S0. So in almost any system that where Boltzmann equation apply, this won't be true. The D of E would be much smaller at very low energies, exponentially smaller. So, and this order of limits is also very important. You first take the system size to infinity, and then you send temperature to 0, and then you find this 0 temperature entropy, which is a pure number that we computed way back in 2000. All right. So this number will be related to black hole entropy in some general sense in a few minutes. So that turned out to be really a key property. When we discovered it, we said, oh, this is unphysical, let's put it in the appendix. Luckily, we put it in the appendix. We could have forgotten about it. All right, but now with the help of brilliant contributions by Kitev, Amaldacena, and Stanford, we can go beyond this large N theory. We can even look at the fluctuations and look at the path integral about this large N saddle point. I just want to, for my future purposes, say a few things about the structure of this path integral. One is that associated with this Planckian dynamics is a certain very large symmetry of the low energy equations, low energy structure of this path integral, and it's a time reparameterization symmetry. So, think of tau as some imaginary time in this case. Sigma is, running at some clock, and sigma is a different clock, and the two clocks are running at different rates. It turns out it doesn't matter. The physics is the same for both clocks. And this is, very reminiscent of the kind of general coordinate invariance you have in Einstein's gravity. So here's a quantum system which has something like general coordinate time reparameterization invariance anyway, emerging at very low energies. Furthermore, if you look at the low energy equations, saddle point of this path integral, it also has a certain conformal symmetry, where f of sigma is this function over here. And this is the feature of the saddle point. And again, this is a mathematical point I'm making, but for the experts, it will come back again when I talk about black holes. All right. Okay. So that's the SYK model, which is so far just a toy model that a few of us just love to play with for a long time. Now I'm going to try to take its insights, and this has been work that's been ongoing to some extent, and apply it to, first superconductivity, where we're going to, we see some tantalizing similarities, but that's far short of actual theory, because the superconductor is not a system with random interactions and no hopping, far from it. So why should it look anything like this model? So I'm going to get how am I doing on time, Leon? 20 minutes, okay. All right, so 10 minutes for superconductors, 10 minutes for black holes. We solve everything. Okay, so this is a phase diagram I've shown you. And many of us looked at this phase diagram and said, one of the, So let me say a bit more about these metals. So you have this metal, ordinary metal here, and all metals have what's called a Fermi surface. In this case, this is what the Fermi surface of this metal looks like. This demarcates the occupied states of the electrons, which are here, with the unoccupied states, which are over there. Now, it turns out if you go on the other side of the strange metal, you get what's called a pseudo-gap metal, and my previous talk was about this, but I won't say much more, other than to say that this is a very bizarre state where it has a different Fermi surface from this one. So this set up the problem, which the whole community has been looking at, is to understand how you could get quantum transitions presumably at some low temperature inside the superconductor between these two types of states. So this is So this is a problem which was originally looked at by Hertz in 1976. And he looked at a variety of problems, but not all of them, where you had, for example, you could have a Fermi surface that has a square-like shape, and it distorts to a rectangular-like shape. And this sets up a quantum phase transition at 0 temperature with some anomalous quantum critical region at finite temperature above the 0 temperature phase transition. Or you could have some change in the shape of a Fermi surface, or you could have a jump in the size of the Fermi surface, which is what seems to be happening in the cuprates. And then now we have, there are 3 different types of quantum phase transitions, and we have, quite well-developed theories of this type of transition. And the big question has been, what do you get near the critical point? Well, you find at 0 temperature, you do get something that leads to breakdown of Boltzmann-Landau theory. You get what's called a non-Fermi liquid with no quasi-particles. But does this lead to the strange metal at finite temperature? And one understanding from a lot of work has been the answer, unfortunately, is no. If anything, it's a perfect metal. And the reason has to do with sort of emergent conservation laws, including conservation of momentum, that emerges in all of these low-energy theories of quantum phase transitions in the presence in perfectly clean systems. So this opens up the problem of, how do you understand the strange metal, if not by this quantum critical point? Well, it seems like our community forgot a basic fact, that even in ordinary metals, to understand transport or resistivity, you have to account for disorder. There's always some impurities, and the impurities do affect the resistance and really almost any property you observe. Now, but in a metal, you can do that in a fairly simple way. But here you have to put in the impurities in a more self-consistent way. But we know how to do that, how to put in randomness in a self-consistent way. I just solved the problem, which is the SYK model, where randomness was accounted self-consistently, and it led to something like what's observed. So that's really what you have to do. Yeah, sorry, this is getting a bit technical for this audience, but anyway, I'll skip through this quickly and then come to black holes. So this is the kind of theory you write down in the absence of disorder, and then you put in some disorder, some random potential for the fermions, but you also got to put in some randomness in the position of the quantum critical point. So this point here, this point here, this SC could be at different locations at different points in the sample, and that turns out to be the most important thing to study. Anyway, so we have done that, and then what we have realized is that if you look in more detail at the structure of the resistivity in actual samples, in addition to this quantum critical behavior at very low temperature, there's also this foot that emerges essentially in all the materials. And what we now understand, this is recent work, as you can see here, is that in this higher temperature regime, you can take a version of the SYK model, which is generalized to 2 dimensions, so it's getting fairly close to the microscopic physics. And if you tune it to the quantum critical point, and that's the tuning you need to do to get rid of the effective hopping in the SYK model, what is very natural, then you do get exactly the observed behavior. Whereas, I'm going to skip this. Whereas this foot requires physics beyond SYK. So the SYK is just too simple. Eventually, this kind of averaging of disorder disappears, and you really have to look at localization effects, which are much harder to evaluate except numerically, and that's still ongoing work. But in this upper regime, let me just flash, you can compute the resistivity as a function of temperature. You get everything except the foot. This is the optical conductivity, the real and imaginary parts, and this is our computation, the scattering rate, the effective mass, all seems to work very beautifully, sorry. Okay, you just have to take my word for it. Well, better than any previous paper, theory as far as I know. So we are pretty excited that there is some kind of 2-dimensional generalization of the SYK model, which builds on this theory of quantum phase transition of Hertz in the presence of disorder, and you combine them in just the right way, you seem to be able to reproduce a lot of the experimental details. Okay, now finally, the last 10 minutes, maybe, let me turn to the other problem, black holes. Now here it turns out quite remarkably, the SYK model is, for reasons I'm going to now explain, much more than a toy model. It's actually not so bad. You don't have to generalize it to some 2-dimensional case. It's almost literally gives you the behavior of certain black holes. Okay, so the question that Hawking's calculation raised was, that's fine. You're doing this computation from the outside of black hole, and you get this entropy, but there obviously have to be some states of whatever is inside a black hole, which reproduces the right density of states to be compatible with the entropy. That is, can you make these two gravestone formulas compatible? Yeah, Hawking's wave only has the temperature, not the entropy, but anyway, I put it there. All right, so this is a question that has been addressed, most famously in string theory, but it's only been addressed for supersymmetric charged black holes. And they get an answer which is actually, to condensed matter physicists, is really bizarre, where, in fact, in this case, they do have a ground state entropy. There's an exponentially large number of states with exactly the same energy. And this is what happens as a consequence of the supersymmetry. But of course, the amazing thing is this S turns out to be exactly right for that black hole. And that was a great achievement of Strominger and Waffa. But it does have this feature that it's rather unphysical. It requires low energy supersymmetry for this to be true. And in fact, if you take the SYK model and take a supersymmetric version of it, you also get exactly this feature. Okay, so we want to look at non-supersymmetric black holes. And we're going to work in 4 dimensions and try to do the calculation that Gibbons and Hawking did. In fact, they did most of it, and it's a bit of a, well, not that much. In principle, they could have done everything I'm going to now show you already back in the 70s, in principle. But the fact remains that this calculation was only done after the SYK model was understood. And I think that has to do with the fact that gravity is sort of an ill-defined path integral, and there's lots of blind alleyways you can go down. And it's only when you have an actual quantum system in front of you to give you an example of what's the right thing to do, then everything becomes clear. Anyway, that's my interpretation of why Hawking already didn't do what I'm going to now describe. So we're going to take a black hole with a net charge Q. So then you have to take the Einstein gravity and Maxwell's equation and look at the solutions of such a black hole. This is the Reisner-Nordstrom black hole, and which was studied in this context by Clifford Johnson and others way back when. So if you look at their solution of this charged black hole, first of all, where does temperature come in? We're going to do this in imaginary time. It just comes in as the circumference of the time, imaginary time, which is a circle in these imaginary time path integrals. And also in imaginary time, the space-time just cuts off at the horizon. It's like the shape of a cigar. So fortunately, you don't even have to go inside the black hole to do this computation. You can just do everything on the outside to compute at least the flotation function in principle. All right, so if you take this imaginary time path integral, now let's look at its low energy behavior. Now it turns out, if you get very near the horizon and look at the solution of the Reisner-Nordstrom metric, it has a factorization which is key to what I'm going to tell you about. The radial direction zeta and the imaginary time tau, separate from all the angular modes. So it turns out all the angular modes with non-zero angular momentum along the direction x have much higher energy. So you could just forget about the angular modes and just look at a two-dimensional black hole. So it's one space and one time. And furthermore, the metric of this near horizon metric is what's called ADS2. It has this form, and that's the shape of the funnel that I was showing you earlier. And this, this is a highly symmetric metric. It's sort of like the metric for a sphere. If you take a sphere, we know you can do rotations, SO3 rotation in any direction. This metric has as big a symmetry. It has an SL2R symmetry of these type of transformations. And amazingly, this is exactly the symmetry of the SYK saddle point. So that's the second indication of the close relationship between black holes and, in this case, black holes with ADS2 metrics and the SYK model. All right. So then you can then take this 3+1 dimensional theory and take the low energy limit, and that leads to what's called JT gravity. in 1+1 dimension. That's along the zeta and tau direction. You have to pull out this overall factor, which is the Hawking result at 0 temperature. So in fact, such black holes have a 0 temperature entropy, just like the SYK model. So that's also great. And then amazingly, this theory in one space and one time dimension, gravity has lots of symmetries, lots of coordinate reparameterization invariance. In particular, in 1+1 dimension, there is no graviton. So you can just actually completely gauge away everything in the center and make it a theory just on the boundary. So this becomes a theory that eventually in 0+1 dimension. And the amazing thing is it's exactly the same theory you would get for starting from the SYK model. So you can get this path integral, which is known explicitly and fully evaluated, the so-called Schwarzian path integral. You can get it two ways. You can start with Einstein gravity and take the low energy limit near a charged black hole. Or you can start with the SYK model and take its low energy limit. You get exactly the same theory. So now we can now work backwards from everything we know about this path integral from the SYK model. We can now actually compute corrections to the Hawking result. So first of all, you can actually now compute the density of states rather precisely. So for the SYK model, previously I told you about this 0 temperature entropy, the exponentially dense density of states. And that's this factor here. Then when you do the Schwarzian path integral, you get the cinch. And when you put in some microscopic information, you get the 1 over n. Various people have contributed to this, and I've just been lazy and refer you to this review article for all the original references, where this gamma is the linear and temperature specific heat correcting the 0 temperature behavior. So that is the full answer for this behavior of the density of states at low energies that comes from the inverse Laplace transform of this integral in imaginary time. So you can do that also for black holes. And this is the final result that in this form obtained finally by Iliusiu-Murthy and Turiachi just last year. This is the Bekenstein-Hawking result. Then this cinch is exactly the form of the SYK model that comes from the JT gravity. And you can even fix the coefficient here in terms of the area of the horizon at 0 temperature. So these are quantum corrections to the Hawking result. And then you get a prefactor, and this is the only thing that actually depends upon the matter content of the universe. And the low energy matter content, this factor of 347 over 90. Yeah, so that's, involves doing this path integral a bit more carefully. And anyway, all right, so that's all. So, there's a remarkable thing. This 1 over n here is the analog of this prefactor. This is this Hawking result is the analog of this S0 that Georges Parcolet and I obtained. And the cinch is the same, cinch square root of energy. Okay, so how do I view this? Well, I view the SYK model, to use a word that now very common. It's a quantum simulation of a black hole. If you're sitting outside, and as far as you're concerned, there's some kind of SYK model, at least for the low energy limit, sitting on the horizon. It's not at a point, it's the L equals 0 mode. This is not to say there's actually an SYK model on the inside. The results that I presented are quite universal, independent of any quantum system with these symmetries. SL2R symmetry, time representation invariance will have these properties. But, this is a start. This is kind of what the inside of a black hole looks like. It's an entangled soup or something. All right. So to conclude, I've talked about quantum entanglement and basic principles of stellar mechanics, how they come together in a very interesting way in theories of superconductivity and black holes. And the SYK model describes multi-particle quantum entanglement, resulting in loss of identity of the particles. I should say this picture has been made by Leon, so thank you very much, Leon. I've been using it without attribution for many, many talks. And there's some generalization of the SYK model, which describes the strange metal behavior of numerous quantum materials. This is our claim from relatively recent work. And in a dual set of variables, this is much better established now, has led to the computation of the low energy density of states of charged black holes. It's also played a role in a lot of work on how, on the Page curve and the evaporation of black holes, which I only dimly understand, but I'm sure you've heard other talks on that. So thank you.
Thanks so much, Sabir. I'm sure we have time for some questions. Matthew?
Oh.
We're not on Zoom or anything.
In the applications to the superconductor,
Yes.
how do you account for the Fermi surface once you put in the disorder? Was that, you just say it's washed out because of the disorder?
No, we do put it in. Sorry, yeah, that's the part I skipped over. So this is the model. So let me just, thank you for the question. So there is a Fermi surface of these electrons right there. And then there's a random mass in the phi, and there's also random potential of the fermion. So it does get diffused, but you do have to put the dispersion in. And what we do in the SYK regime is we say that the states are still extended, and so we can account for this delta S by just moving it over here. And so then you get a random coupling. And now you can treat this model. This is the full model that we actually solve in this kind of SYK type approximation. So all of these results here, like this conduct, they came from the full solution of the self-consistent Eliashberg type equations, or the SYK type equations of that model. So what happens is that it's really a model of coupled bosons and fermions. The boson has a diffusive type propagator at the critical point, and the fermion have marginal Fermi liquid behavior, and so on. That all comes out.
Restructuring of the Fermi surface, is that something that...
Okay. So this is in the quantum critical region. I'm not talking about what happens on the other side. Yeah, that's a whole different thing. So in this phase diagram, yeah, so the bottom line then we think is that, in this regime, you really have to, disorder plays a really central role to understand basically any property. But once you move out in the pseudo gap or whatever it may be over here, then it's not as important. But the quantum criticality is entirely controlled by disorder.
Okay, we had another question over here.
Sabir, in your slide with the optical conductivity.
Yeah.
Beautiful agreement with your theory, or at least more beautiful than before.
I went very quickly, yes.
You went quickly. One thing I caught, but I noticed was there's a limit to the quantum criticality. There's a scale on that slide. I think it was something like 0.
It's a great question. Yes,
0.4 eV. What's that all about? Why should there?
That is an error in the experimental paper. I talked to them. They're going to correct it soon.
The review article.
No. So this paper, I talked to Doug Pondamero.
Right.
So it actually shows up more dramatically right here. If you look at this.
In figure B, so it says 0.4 eV, there's an upper bound where you can do the scaling.
Yeah. This scale is wrong because they didn't estimate the value of this coupling K correct. What they compute is the conductivity.
Of course.
The time is a derived quantity.
Of course.
And they made a mistake in computing this K. So this shows up more clearly here. There's many experiments that show that h bar over t over kBt is about a 1, where they're getting it to be about a 5 or 10. That's just wrong. In our theory, that's actually about a 1. That's what we get.
But in terms of the cutoff that they give of 0.4 eV, what sets that scale?
Well, that will also change once they change the value of K. They have to estimate this K to get from here to there.
But I mean, the existence of that scale, what sets that scale? Maybe that's...
This K is like the plasma frequency. It's the integral over the whole conductivity.
And it's only 400 MeV.
I don't know what it is.
Or whatever, on that order.
Yes, per layer or something. Yeah, you have to also put the layer spacing.
It's fancy.
I have an email from Dirk, if you want to see it, saying he agrees there's a mistake, and I'm going to urge him to write an errata.
That'll move that scale, but the existence of the scale won't go away.
No, this will be smaller. This won't be 0.4 eV. Maybe it'll be 0.04 eV or something like that.
Tony?
What is the charge of the black hole corresponds to in the SYK model, and what stops you from taking Q to 0 and study the structure?
It is literally the charge of the SYK model. So in fact, I use the same symbol. So if you take the SYK model, I had this Q here, this Q between 0 and 1. So if you look at the equation of state,
Q is the number of fermions.
it's the fractional occupation. So the dependence of the entropy as a function of Q, which I didn't show you, for a black hole in the SYK model also match. There's lots of features which are very similar.
So what prevents you from Q to 0
Then this dimensional reduction doesn't happen anymore. That's the problem. I mean, so why? Gary will explain that to you.
You need to be near the maximum possible charge of the black hole to get this symmetry, this ADS2 region.
Well, another way to say it is low temperatures or low energies. It's the same statement. But this factorization, near horizon metric is ADS2 cross S2. That does not happen at Q equals 0. That is why the Schwarzschild black hole problem is still unsolved. It's a much harder problem.
Sorry, really kind of dumb question. I mean, how literal is it? Is there really the same physics going on in these two situations, or is it an analogy?
Well, I think it's closer to the first, because I think this is maybe this last picture is a better way to think about it. If you look at low energies for a charged black hole, unfortunately there's no charged black holes out there, but there could be in principle. Low energies for a charged black hole or low energies for SYK model, it's literally the same equations in motion, except they're in very, very different variables. They're highly non-local change of variables that you have to make. So if I did an experiment on an SYK model, it's not so easy for me to translate that to, not directly anyway, to what would happen for a black hole. When people are trying to build a wormhole with two SYK models with quantum devices, they haven't gotten there yet, but I think there's some hope of getting analogous behavior in SYK model to wormholes in gravity. Now, this doesn't mean that there's actually a physical wormhole that you will fall down into, because you don't have access to the gravitational variables in the lab.
Yeah, so I might be looking at it in a incorrect fashion, but so we discussed how this quantum effects should play a crucial role in in changing the Boltzmann equation, right, in these metals. But the current story with the Yukawa SYK theory, right, there I guess the disorder is playing the role of, so how are we reconciling these two factors?
Well, so let's see. So the starting point of that theory in equilibrium of the Yukawa is not so different from these equations, except you also have a momentum, you have Green's functions for fermions and bosons, but there's some set of self-consistent equations for the whole Green's function as a function of frequency. And then when you do perturbations, you have to transport or even nonlinear transport that Pavel talked about. Then you have to look at the generalization of this. And the generalization of this is very similar to the so-called Kadanoff-Prange equations. You get some generalized version of the Boltzmann equation where you have distribution function that depends not only on position and momentum, but also on frequency. So it's a much harder set of equations to solve. But there are certain regimes where you can use those types of equations.
So I guess it's combined effect of disorder and the fundamental changes that need to be done.
Well, I mean, so these are great questions, and so like I said, there are these two regimes. So all of that, what I'm telling you about is over here. When you go to the foot at very low temperature, the disorder becomes very strong, and there is no more self-averaging. You can't do that anymore, and you have completely different physics, which cannot be described by SYK model. And I think the major open problem in my mind is to now understand how you go from here to here, and maybe even have experiments that can detect this crossover.
If I can make a plug, just if you want to learn more about some of this, several of Subir's collaborators gave talks in the program that just is finishing up this week, so you can go to KITP's extensive archive and watch a talk by Peter Luntz or Avishkar. You get a lot more detail about that particular thing.
Thanks for the great talk. So I think the match between the partition functions of the two sides suggests that the large N low temperature limit of SYK is a good model for lower dimensional gravity outside the black wall.
Yeah.
One could consider the 1/n corrections of SYK. So what kind of gravitational aspect one would expect from that? And also, is there anything that one can learn more from SYK side about the black wall interior?
So this formula is well beyond 1/n. This also includes e to the minus n corrections. So this path integral, so there's an n out front here, or g, or the area of the horizon. This path integral can be evaluated exactly, including all the exponentially small corrections. And there are certain extra corrections of black hole at, so if you look at the SYK model, I should have put a dot, dot, dot. There's a term about a t to some power, t to the 3.4 or something over here.
Yeah.
That will lead to corrections which are further, next corrections here. Those are not part of the gravitational theory. But everything I've shown has a direct analog in the gravity theory.
But should I think of it as corrections to JT gravity?
I don't think so. That's my guess. I don't think so. I think that's, at that point, you're really sensitive to the UV, and you're getting UV physics of the SYK model. Some people say, well, there must be some gravitational dual. But what? I mean, is string theory theory of gravity? No, it's a theory of strings. I mean, when we say we want a quantum theory of gravity, we want a quantum theory whose low energy limit is gravity. And by that criterion, SYK model is a theory of gravity.
Thank you.
Okay, I think we should probably give Sabir a break. He's been talking more or less nonstop for, I don't know, 3.5 hours, something like that. So let's thank Sabir again for a wonderful talk.